Welcome back as we begin to discuss the topic of seal selection. In the usual course of events, the new seal we fit would bear the same part number as the old one removed. Most seals have a part number etched or molded onto the casing. However, it is important that you are able to make a seal selection from basic principles, especially if you have no old seal to relate to. There are basically 4 considerations to make, namely, the size of the seal, the shaft speed, pressure against the seal, and temperature of operation. Let us first consider the size of a seal. Seal descriptions relate to 3 dimensions, namely the shaft diameter, the seal housing or bore diameter, and the depth of the seal housing. All dimensions are given in millimeters. If you supply such information, then a suitable seal size can be obtained from your local supplier. All oil seals are made to have an interference fit within the housing. This means that the seal's physical outside diameter, when measured, will be slightly larger than the housing bore diameter. This interference figure, or difference, is normally in the region of 0.25 to 0.3 millimeters for molded seals and 0.1 to 0.15 millimeters for metal-cased or assembled seals. The next consideration is shaft speed. Nearly all standard rotary shaft oil seals are limited to shaft speeds of a maximum of 18 meters per second. However, on shafts below 35 millimeters, the revs per minute are more critical and they should not exceed 7,000. Regarding pressure, again, standard oil seals are limited to maximum values. Pressure in excess of 0.5 bars will tend to exert heavy loading against the sealing lip, resulting in rapid wear as the lip breaks through the oil film. In extreme cases, the sealing lips can be blown inside out. There is not much the artisan can do if pressure ratings are high, except in certain circumstances to fit a backup ring under the strict advice of your local seal experts or dealers. It is advisable to check the machine for problems such as clogged vents or breathers. Such a condition will cause high internal pressures, and this is a common cause of premature seal leakage or failure. Our last consideration is that of temperature, bearing in mind that any synthetic rubber exposed to temperatures beyond its capabilities will become hard and brittle. This not only destroys the seal, but can seriously damage the shaft as well. Several synthetic rubber compounds are used in seal manufacture. Some of the names will become familiar to you as you work more with various equipment. Materials such as nitrile, polyacrylic, silicone, and fluorocarbon are typically utilized today. The majority of oil seals made for general applications are of nitrile, which is identifiable by its shiny or glossy black appearance. Nitrile seals are suitable for most applications that do not exceed temperatures between -20 to +100 degrees Celsius. More suited to higher temperatures, up to 160 degrees, are polyacrylic seals. Such seals can also cope with extreme pressure lubricants, as used in some vehicle differentials. Next are the silicone seals, popularly used for automotive engines, where high speeds and high temperatures are encountered. Some applications, especially in the chemical industry, require materials that can withstand very corrosive conditions and temperatures between -20 to 200 degrees Celsius continuous operating. Specially developed fluorocarbon materials are produced by leading seal manufacturers, but the cost of the seals can be as much as 30 times more than nitrile. A popular trade name for such a material is Viton by DuPont. For practical reasons, we suggest that you consult your local dealer for advice whenever you are in doubt about seal selection. After the break, we shall demonstrate installation procedures.